Good morning. So, before continuing to the new lesson, if you remember, we had one problem that I didn't solve before leaving the lesson. So let us just start working on that to refresh your memory a little bit. So my goal was to know how many numbers, how many 4-digit numbers are there, so that the sum of the digits of that number is an odd number. Yes? So here, for example, 1, 2, 3, 4. 1234 is a 4-digit number, but is it acceptable for us here? To see that, we have to add the digits. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 6 is 10, and 10 is even. So we have to cross it over, yes? But on the other hand, 1, 2, 3, 3. 1233 is acceptable, yes? Because it's a 4-digit number, but if I add the digits, it becomes 9, and 9 is an odd number. So this is acceptable, the other one is not acceptable. Okay, we want to find the total number. Okay, so writing a 4-digit number can be viewed as a 4-stage task, yes? So then I would say that, okay, let us choose the natural order first if possible. So I will take the first stage to choose a number for the leftmost digit here. So how many options? So let me write it like this. I have 4 positions to fill up. I know the goal. The goal is to have a 4-digit number so that the sum of the digits is an odd number. So let me, for the time being, let me keep the natural order. Stage 1, stage 2, stage 3, and stage 4 to see if it works or not. And of course, let me just review this. Sometimes the natural order doesn't work, but if you change the order, it might work. And sometimes even if you change the order, it will not work. You need more rules and more principles, yes? Okay, I would say that the first stage is the easiest one. Let us see if it works or we come to a dead end. Okay, because of that independence. Do you remember? Each stage should be independent of how the previous stages are done. So, stage number 1, we don't have any problems. How many options are available for stage number 1? How many? 9. Except 0. I can choose all the digits except 0. So there are 9 options here. And if you don't mind, let me just write the digits in front of you. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the only options available. Except this one, I can choose whatever I like. So there are 9 options there. But now when you go to stage 2, you need to think in this way. Let us assume stage 1 is done. What is the meaning of that? It means that I have chosen one of my options for stage 1. Let us say I have chosen I have chosen 1. Then how many of them are left for me for stage 2? 10. Assume that no, I have chosen 4. Then how many options are available for stage 2? Again 9. Sorry, 10. Yes, there are 10. Yes, so it doesn't matter which one of these numbers I have chosen for the first one. Independent of which one I have chosen, I have 10 options. Well, of course, you are a little bit concerned about what happens if the sum is odd. But let me just give you my strategy. So for the time being, I have 10 options available. So at this stage, you really don't need to be worried if the sum of the numbers are odd or not, because we haven't done yet. Yes? Okay, now how many options are available for that one? How many? Yes?
For this stage, it depends.
It doesn't depend, does it?
It feels like it does.
No, I understand your concern, but your concern is that you want to make the sum to be an odd number. Yes, but still what I'm saying is that, for example, let me choose 1 here let me choose 8 here. Okay. How many options you have available so far?
10.
Still 10. Yes, the hard part is the last one, if it is going to work or not. Yes, so then I have 10. Yes, but now can you tell me how many options are available for stage 4, because I have also one constraint. The constraint is that the sum of the digits should be an odd number.
5.
Okay, this is 5. Yes, yes or no? But what is the reason that you said 5?
Because there are 5 odd numbers, and if there is an odd number in the 4 digits, then the sum will be an odd number. There's only one.
No, because that is the problem. We don't know which one we have chosen so far. We might have a mixture. That was probably Kevin's concern, yes? So we have a mixture. We don't know. Have I chosen 2 odds here, 2 evens, 1 odd, 1 even, and mixture 2 evens, 1 odd? You know, we don't know what we have done so far. That is the reason we have written 9, 10, 10. Yes? So that is interesting. So your answer is correct, but your justification was not that. So this is 5, independent of what I have done so far. But why? Yes?
Because there are different options for those 3 numbers.
Mhm.
Either they're all even and then the last one has to be odd.
Mhm.
They're all odd and the last one has to be even.
Mhm.
There's 1 odd, then the last one has to be even.
Yeah. Let me make it simpler. So it's exactly what you said is correct. But let us, instead of considering all combinations, let me consider the sum so far. Yes? I have chosen 3 numbers here. There are 2 possibilities. Either the sum of these 3 numbers is even, or the sum of these 3 numbers is odd. If the sum of these 3 numbers is even, what should I choose for the last one?
Odd.
To make the whole sum even.
1 odd.
Sorry, that's to make the whole sum odd. I have 5 options. Yes? So let us consider this. Let me consider the sum of these 3 numbers, for example, to be capital S. There are 2 things happening for me. S is even, S is odd. There are only 2 options so far. I add these 3 numbers that I have chosen so far. It turns out to be odd or even, nothing else, yes? If the sum so far is even, to make the whole sum to be odd, what should I choose for the last digit? An odd number, yes? But how many options are available for odd? 1, 2, 3, 4, and 5, yes? But it turns out that sometimes the sum so far is odd, and I want to make the whole sum to be odd again. So then how many options are available for that one?
5.
5, but this time it is 5 again, but these I have to choose the even ones. Is that understandable? So this means that again this is 5, so that is a little bit a coincidence. So, but of course, I have 2 different types of numbers that I can put here. Either I have to choose odd numbers here, or I have to choose even numbers there. But for odd numbers and even numbers, the coincidence is that the total number of even numbers and odd numbers are the same, so it doesn't matter. And that is exactly what you might expect. So I multiply them, and I get 4,500. But the strategy is nicer. I want you to think about it in this way. Otherwise, you need to consider different scenarios and calculate the number of items in each category and start adding them up. But of course, this is a better way of calculating. Any questions here? Is that understandable? But I also told you that if I ask you how many of them are there so that the digits are all this thing, then it becomes hard. And then you have to consider different cases. This will not work in that way. Yes? Okay. Any questions so far? Okay, another question. Let us refresh you a little bit about things, and then before going to these very simple rules again. Yes? Assume that in a classroom, for example, you have 10 numbered chairs. So you have 10 numbered chairs, okay? from 1 to 10. And now assume that you have 3 students. So let us consider it in this case. I have 10 numbered chairs in a row from 1 to 10, and I have only 3 students. In how many ways I can let these students sit on these chairs? In how many ways? This is a simple problem. There is a reason that I am bringing it up, and you will understand why. It's not hard. So I have 10 chairs, imagine. By the way, whenever you can arrange the students, in principle you should be able to count the number, yes? If you are a teacher and there are 10 seats in a row, and I have 3 students, and it is very easy task for me to assign chairs for students, yes? Okay, I can say Kevin sit down here, I don't know, Dennis sit here, and then I'll call sit here, yes? So when I can do that, it means that I should be able to count it. If I just think what process is going in my brain, yes? What do you think when I say that, okay, Kevin sit, I don't know, in chair number 5, and then I assign another chair to someone else, another chair to someone else. So what is the task here? Can you define it? The task is clear. Assigning 3 chairs to 3 students. Yes? So how many stage task is this task? 3. Yes? So stage number 1, what can I call it? Stage number 1, assigning 1 seat to 1 student. To the first student, yes? So how many options are available? How many seats I can assign to the first student? 10, yes? And then think about it in this way. Stage number 1 is done. It means that one of the seats is now occupied. And then I have another student. So student number 2, how many options will be available for student number 2? 9. And then after these 2 are done, by the way, is this 9 independent of how I have done it here?
Yes.
Yes. And then stage number 3, how many options will be available? Because so far 2 chairs are occupied. And then how many are left? 8. Yes? Okay, so I hope that you agree with me. The answer to this question is 10 times 9 times 8. Yes? And of course, what is the number? 120 ways. Yes? Is that clear? But let me change the scenario a little bit. This is from my experience, then people get a little bit trouble. Let me change the number of chairs to be 3 and the number of students 10.
Okay.
Of course, it is clear that there are not enough seats for all students, but let me just do it like that. I have 10 students. I don't need to say 10 number the students because the students are distinct. 10 students in a room that there are not enough chairs for everyone, but there are 3 chairs. And I want, of course, choose 3 people from the group of the 10 students and let them sit on these 3 chairs. Now how many ways I can do that? The people at home, if you write something on chat window, I will not be able to see it. Please say something. I will try to hear from the poor loudspeaker. Yeah. Okay, what's the answer now? Yes?
I don't know the answer, but I think I know the strategy.
Yes. So can you define me the task? So just imagine the scenario. There are 10 students here impatiently waiting to get these chairs, yes, because they are so tired probably Monday morning, and they want to get the seat, yes? And then you were thinking about, okay, what is the task here?
The task would be picking 3 unique students.
3 students.
To sit in each chair.
Yes. So that's a how many stage task again?
It would be 3 stages.
Yes.
But
there are 3 stages again. Yes. You can say that. Okay. Can you describe? Okay, I can see it as a 3 stage, but how? Can you tell me something about in your own words? What do you say would be stage 1?
we have 10 students to choose from. So stage 1 would be.
No, if you want to write it as a 3-stage task, what sentence you write for stage 1? In your own words, of course.
Choosing the first student that gets to sit down.
No. In that case, you will. Okay, because that is not the problem. Because as soon as you choose the student, the task is not. The stage 1 is not done yet. Because you have some options for choosing your student, but you also have some options to assign one of the 3 chairs to the one that you have picked up. You understand me?
Yes.
That's extremely important. If you want to be successful in combinatorics, you have to have a very clear strategy in your mind to be able to do that. So when I ask you to write stage 1, if you say my strategy is to choose a student, and then of course then you need to continue because there are 3 chairs left for you and 1 student in your hand, and then you want to make that student there, yes, as soon as you can. Okay, but then how you do that? So that is, if you want, of course, you can write the whole sentence, or you can change your strategy.
I mean, my first thought was that we need to use the sum rule.
No, there is no sum rule yet.
But I don't see any other way.
Yes, there is. And that's exactly the reason that I brought this up. Because I don't know, based on my teaching experience, students doesn't have any problems solving this, but they have a little bit of hard time to solve that. I don't know. It is
isn't
clear.
it the exact same?
Yes. So Jakub is saying that that would be exactly the same number. Yes, and I agree with you. Yes? And that would be exactly the same number. The reason is that you think humans are better than objects. Yes? For mathematics, mathematics doesn't care which one you call human, which one you call objects. Yes? But I don't know, for some reason we are taking this for granted, we are better than chairs. Yes? And then of course you have some hard problems. For a student, so from a mathematical point of view, you have 2 sets of objects. And then you want to do the same thing. Yes? Or if you don't like it yet, still you feel better than chairs. So to be better than chairs. But let me tell you what would be strategy 1 here. I would say strategy 1 is to choose a student for chair number 1. Okay? So I have 3 chairs in front of me. I have 10 students there. I do not start with the students. I start with chairs. I assign a student to chair number 1. How many options are there? 10. Yes, I have 10 students. I want to pick 1 student for the first chair. So then if you look at it in that way, stage 1 is still 10, but the reading here and the reading there are different. Yes? So then stage 2. So assume that the first stage is done. What does it mean? It means that I have chosen one of my students and I have filled up the first chair. And now I go to the second stage. It means that I want to fill up the second chair with the remaining students. How many of them are there? 9. And the next one is 8. And then you see the answer is exactly the same. So yeah, so I don't know. This is my experience that people understand this easier than that one. But now hopefully you understand. There is no difference between you and chairs in mathematics. Yes. Okay. Now, of course, the sum rule, that the next one, is also a very simple task. You know when to add numbers. But this is my experience again. As soon as I start teaching you this, then sometimes you become doubtful about when I have to add and when I have to multiply. So if you don't believe it, you need to wait a little bit. Okay, so here, what is the sum rule? So assume that I have a task. It is not a two-stage task. Well, I don't know, it's just one-stage task. But I can do it in two different, completely different ways. Yes? But let me just give you an example. For example, you have a city here, another city there. If you want to travel from city A to city B, you have two roads. Okay, so you can take your car and drive from A to B, and there are three railroads, so two roads and three railroads and 5 airways, I don't know, or whatever, or airlines, for example. Yes? Yeah. And then you want to travel from A to B. Of course, I cannot say this is a three-stage task. The task is travel from A to B, finished. Yes? But I have three categories of options in front of me. Yes? I can go from A to B driving a car or using a train or using a plane. Yes? There is an or between them. Yes? I go from A to B either by my car, finished. The task is finished. Or I choose a railroad, the task is finished, or I use I don't know, I go by flight. So, and I ask you the same question. I ask you the question: in how many ways I can go from A to B? 10. Here you add them. Is that understandable? So the number of ways that takes me from here, I would say that I can choose to drive, but I have two options. Or I choose to go by train and I have three options, or I choose to go with flights. I have 5 airlines, yes? So then I will have the number, so that would be 10 options. But remember, this I cannot say this is a three-stage task. It's one-stage task, yes? But the task is categorized into 3 different ways. And then I know how many ways I can do each one of them, then I add. Yes? Is that clear? So from set theory point of view, it is very clear. So if you want to, if this is the universal set, let me call it U, and if you want to calculate the cardinality of U, of course there is one way to count all of them without any kind of organization or number or any discipline, but you can just do it like this. For example, you can partition your rectangle into different distinct parts and count the number of elements in this part. For example, let me call it A1, A2, A3. So in set theory language, A1, A2, and A3 are subsets of the universal set. And I have drawn them like this. There is no overlap. It means that A sub I intersection with A sub j for whatever I choose for I and j. Of course, I should be not j. So it means that if I ask you what is the intersection between A1 and A2, nothing. Intersection between A1 and A3, nothing. Intersection of A2 and A3, nothing. If this is the case, and still I want to find the cardinality of U, what should I do? I can calculate the cardinality of the first bit, calculate the cardinality of the second one, or the third one, and then I add them. Yes? That's the sum rule. Having no overlap between these distinct parts is actually very important. Do you remember? If I have n, the number of A union B, do you remember it is the number of elements in A? Okay, so might be I haven't used this symbol. Let me just use the cardinality symbol. So if I ask you what is the cardinality of A union B, do you remember from set theory what was it? In general, it was cardinality of A plus cardinality of B,
Yes.
but minus cardinality of N intersection B. So you see, in that case, the sum rule doesn't work. If I want to have the sum rule only, it means that this should be empty. In that case, this becomes 0, and then I will say that the sum of the union is equal to the sum of the cardinalities of each set. Yes? So that is the sum rule. So this we can say that we have a task. It can be done in ways that cannot happen simultaneously. Yes? And then if you can't, this is important, they cannot happen simultaneously. If I choose to drive, then I lose the opportunity to go by train as well. Yes? So this means that the task is done if I start doing it. Okay. So now let me give you another example. For example, let me just start with these roads. For example, you have here, I have 4 cities. Let me call it A and B. And then I have a C here and a city there. And then I have these type of roads. All of them are two-way roads. Of course, this doesn't matter here. So here I have 2 roads from A to C. I have 4 roads from B to C. Yes. And then I have 3 roads from A to D. And then finally I have, for example, 5 roads from B to D. So assume that we have this scenario. My goal is to go from A to B. My goal is to go from A to B. In how many ways I can do that? There are no constraints. I want to start from A, take my car on one of these roads, go from A to B. Yes, of course, then there is no need to say that I have to pass. I have to pass either from C or D. But my goal is to reach from A to B. In how many ways I can do that? The goal of this question is telling you that sometimes the sum rule on its own is not enough. The product rule in its own is not enough. You have to combine them. Yes? That is actually important. But that's a very, very simple example to demonstrate this in a very nice way. Okay, I want to wait for you. In how many ways I can go from A to B? Yes?
Should I say
Just the answer, the final answer.
23? I believe, I'm not sure.
23. Okay, let us wait.
Yes, it's true.
Yeah, it's true. There's another guarantee. Yes. Okay, I think it's true. But what is your strategy? Let us try to understand the problem. Your goal is to go from A to B. You can say that I can go from A to B in 2 different categories of ways, yes? Either I like city C and I go through C and reach to B, or I don't like C, I want to go through D and reach to B. So you see, I am saying or. Okay? And are these things happening together? Can they happen together simultaneously? No. If I have chosen C, then I lose the opportunity to simultaneously go through D as well. That is the whole point. Either, I have to decide, either to choose this option or the other option. They cannot happen simultaneously. That is the key word. That's the key phrase, yes? Okay, but now I would say that, let me see, I have 2 different ways. So for example, if I want to give you a little bit of picture, geometric picture, I would say that let us consider all possibilities in this rectangle. For example, I just want to a little bit explain more here because I want you to understand. A, B, C, D, E, F, and then I have G, H, I, and J, K, L, M, N. So these are the rows. Okay, one possibility is, for example, I can write AC. What does this mean? This means that I have chosen this road and that road, then I am done. This is one possibility. Do you agree? Okay? I don't know. I can just choose B, F. I can choose G and N. So this means that what is AC means? What does AC mean? It means this trip. BF means this trip. And then GN means this trip. Yes? So they are not very organized in this rectangle. Then it would be hard to count. But if I want to do them organized way, I can see that all these items can be divided into two subgroups. Okay? I'm not drawing the picture to scale. Yes, might be the number of items here is smaller than that one. I don't know. I just know that there are two different types of items. For example, I put AC on the left, but if I want to choose GN, I do not put it on the left, I put it on the right. Yes? And I don't know. Here, I can write BE, one option, and then I can write HJ here. So this is the way that you imagine. And I hope that you agree that this way of thinking is partitioning the whole set into two disjoint subsets. Okay? So it means that if I am able to calculate the number of elements here and the number of elements here, in order to know the number of elements in the total rectangle, I am allowed to add because there is no overlapping between them. Yes, again, I am explaining too much because it is trivial, but try to think in this way. Okay, so now for calculating the number of items in this part, I have to use the product rule. Yes, because here I want to go from A to B through C. So it means that I have to choose one road from A to C. In how many ways I can do that? 2. After this is done, and I have to choose one road from C to B. In how many ways I can do that? 4. So, what is my task now? My task is to go from A to C and to B. So this is a 2-stage task. Choosing one road from A to C, I have 2 options. And after this is done, I can choose 4 independent of my choice here. So this becomes 8. So the number of items in this rectangle is 8. And for the same reason, the number of items in the next rectangle is how much? Let me write it here. Is how much? I have 3 options here. So I have to choose one road from A to D, but the task is not finished because if I don't continue, I will be here. But my goal is to go to B. And then how many options are available here? 5. And then this becomes 15. So the total number that is asked in the problem is the sum rule now.
That's 20.
So because this becomes 23. Is that clear? So that is the meaning of the sum rule. Okay. So let me ask you one more question here. Let me repeat this again. So how many four-digit numbers are there? Of course, this is very simple. I'm just reviewing things. How many 4-digit numbers with distinct digits? Because that is very simple. With distinct digits are there? How many of them are even? Let me write odd first. How many of them, of course this is, how many of them are even? Okay, I will give you more examples that you can think about it, but let us do this together. How many 4-digit numbers with distinct digits are there? It's very, very simple task, yes? So can I choose the natural order? So let me choose the natural order if possible. So stage number 1, stage number 2, stage number 3, and stage number 4. I want to write a 4-digit number with distinct digits. In how many ways I can fill up this? How many ways I can write the leftmost digit? 9. Now, in your head, imagine that the stage 1 is done. It means that you have chosen a non-zero digit for this one. But because the constraint is distinct digits, then you need to be careful about how many options are here? 9 again. Because this time, I cannot choose the number that I have chosen, but still I can choose 0. So still I have 9 options. Agree? So I put 9 here. Is this 9 independent of how I have done this stage? Yes, you have to imagine yes. Now I go to stage number 3. How many ways are there? How many options are available? 8. Yes, is this 8 independent of the ways that I have done these two tasks? If you think the answer is yes, and when I go there, what's the answer? 7. Okay, and the answer to the question mark here is 9 times 9 times 8 times 7. Yes?
Yes.
And then you can calculate it. It's good to write with the calculator.
45.
What? Did you calculate the whole?
Yes.
4,000.
4,000?
36.
30?
536.
Oh, 536. 4,536. Okay, so now we want to answer the second one. How many of them are odd? Okay, so it means that I have the same scenario. Okay, now which stages do you prefer? Do you prefer the natural order? Let me just review this a little bit because this is important. Assume that you still insist to do the natural order. If you want to do it, what happens? Okay, so let us, for the second part, let us choose the natural order. In the natural order, let me ask you one question. What is the number of ways that I can fill up the first gap? It's 9. And how many options are available here? How many? This one? It's 9. And how many this one here?
9.
It is?
8.
8.
And then 4.
But it is not clear, is it 4 or not?
Oh.
Yes? Is that understandable? Because I want to have an odd number here. And it depending on how I have used the numbers so far, I have a little bit of problems to know. So it means that the natural order doesn't work apparently. Yes or no? Is that clear? I can write 9, I can write 9, I can write 8, but when I want to have an odd number, I know that I have to choose an odd digit here, but I don't know how many odd digits I have used so far.
Yes.
So this number will depend to the way that I have done the previous stages. So apparently the natural order will not work.
Yeah, so we did that.
So there is another option. Is it a way to change the number, the order, and solve the problem again? If you have enough experience from the past lessons, the answer to this part is yes. So I will take this one away, and I told you that a rule of thumb, it's not always working, but most of the time it will work. Choose the first stage, the one with more constraints. Yes? So which one do you prefer to choose as stage 1? How many of them will have
Stage 4?
Yes, this one. This one I will take stage 1.
Yes.
Yes, because I have more constraints here. Is there any one with constraints? This one. So let me choose this one, stage number 2. And then apparently it doesn't matter which one you want to choose as stage 3. Let us see if it works. It's not guaranteed, but this is just a rule of thumb. Okay, now can you tell me how many options are available here? So let me write the digits in front of you. 1, 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. For this one, I want to have an odd number, so it is clear that I have to choose an odd number here. What is that? I have 5 options. 1, 3, 5, 7, and 9. I have 5 options. Now assume that one of them the stage number 1 is done, it means it means that one of these numbers has been chosen. So let us assume that this has been chosen. Because the digits are supposed to be this thing, I have to cross it over from my list. And then I go to stage number 2. How many options are available? 0 cannot be chosen. For example, 3 has been crossed over. So how many of them are left? 8. But because I need to have distinct digits, it means that one of them from my list is gone. Yes? For example, I don't know, 8 is gone. Yes? And then how many options are available here? 8 again. And how many options will be available here? 7. But of course, in any stage, you have to convince yourself the numbers that you are writing is independent of how you have done the previous stages. And then, so the question mark to this problem is what? 8 times 8 times 7 times 5. So what would be the answer here? 40, 280, yes?
2240.
What?
2,240.
40, yes, thank you. So this is another repetition of the previous lesson. Sometimes the natural order is not the best choice, the best order. If you change the stages, then probably you can solve the problem. Of course, for the second problem, you already know how to answer. Can you tell me, without any product rule, without any rules that we have learned so far, can you tell me what to do to find the answer to the second part, the third part? Subtract. And that is the complementary rule that we will study later. But here I want to avoid them. But of course, I go to scratch paper to double check, because that is intuitively. I have these many numbers. These 2,240 are odd, so what is left is even, yes? So let us check. 240. So how much is that? 6, 9, 2, 2. Of course, you see a symmetry here, and that is reasonable. Yes, we will talk about that. The numbers are not the same. Yes? Okay, but let us try to avoid this type of calculations. We will learn that about this. This is called complement rule. But let us stick to this product and the sum rule. Okay? So, let us go to stage, the third part. Let us go to the third part. To the third part, so now you have a little bit of experience not to repeat things. So hopefully, if you are just new to the subject, you might start with the natural order, but for the same reason you will see that the natural order will not work. Then you will remind my rule of thumb. You might think that let me choose it like this. Do you think still this will work? For this case, how many of them are even? So how many options are available here? This time, I want to have odd and even numbers. Yes? Yes, so here you see how many options are available for S1. I want to have even numbers. I have 5 options. Then when I go to stage number 2, it was easy to do it for the odd case. But when I go to stage number 2, can I write 8 here?
No, because
The problem is that it depends to my choice. Yes? Because when I write 5 here, it happens that I have chosen 0. And then how many options will be left for me for this one? 9. So this becomes 9. Or if I have chosen 2, it would be 8. Do you understand that? So you see that for the even one, even changing the natural order to this artificial order still is not enough to solve the problem. Is that understandable? Yes? This is important. So, I just want you to understand that. You see, here I started with the natural order, it was enough. I started with the natural order for this case, it was not enough, but I rearranged the order, it was enough. But now here, still I rearranged the order, but it is still not enough. So then what to do? Probably I have to consider how many cases? What is the problem here? The 0 is my problem. So I can divide it into two groups. Either I have an even number with the units digit 0, or I have an even number with a units digit not equal to 0. I have two categories. And then I have to use the sum rule. Yes? Yes or no? So let me just write it here. If you imagine the rectangle, the rectangle is this. The rectangle is your question mark. But you can divide it into two categories. The numbers, 3-digit numbers ending with 0. Yes, 0. You have a 4-digit number ending non-zero. Yes, this is the way that you can imagine. But the important thing, because I am going to use the sum rule, I have to be confident about one important thing. There shouldn't be an overlap. Is there any overlap between these two parts? No, because these are numbers with the units digit 0. These are numbers with the units digit not equal to 0. It is clear that none of them is in both of them. Yes? Okay, now can you calculate the number of elements here? Let us use this idea. So the first stage, 5. No, 0 is here, 1. So it means that I have to put 0 there. So how many options are there if I want to put 0? 1 option.
Yes.
And then I jump here. 0 has been used. So how many options are available? 9 for here. And one of them is also used now. How many options are available? What? 8 and then 7. So you multiply them. So how much is that number? Can you help me?
504.
504. Thank you. And now I go here. So how many options are available for stage number 1? I want to choose a non-zero but even, of course. Yes? 4. Yes? 2, 4, 6, and 8. So I have 4 options available there. And then after that I jump to stage number 2. So how many options are available? 8. Yes, because I have used one of them, for example, and now I cannot use 0, so I have to use one of them. So one of them is also crossed over. But for the next one, I can use 0. How many options are available? 8 and then 7. Yes or no?
Yes.
Okay. And then can you help me to answer this one as well?
It's 1,792.
What?
1,792.
92. Okay, my question mark is the whole thing, the total number of items in the whole rectangle. So I have to add them up. Yes? So the answer to the question mark using the product and the sum rule is 504 plus 1,792. So this becomes 6, this becomes 9, this becomes 2. And that's exactly the number that you could predict. Yes? It was, of course, if I give you this in the exam, for the third stage, I myself always use this method instead of going to the trouble to calculate this. But I just want you to understand how to use these rules, because they are actually very delicate if you don't understand them. Especially you start double counting and things like that. Is that understandable? Yes? So all of these examples are very simple, but you need to learn how to think in this new way. So now, because the complement rule is so simple, you can consider what is the idea of complement rule. Yes, if you want to calculate. So the complement rule is this: the number of desired items. Yes, the number of desired items is equal to the number of the total number minus the number of undesired items. So that is called the complement rule, yes? And of course, it is completely natural for us at this stage. But we are looking into it a little bit deeper to be able to solve harder problems. And by the way, I want you to feel it again, that we are solving, even though the statement of the problems are simple, but we are doing some non-trivial examples, yes? It was not that easy if you want to just answer the questions without having an organized thought, yes? Okay, let me now ask you one question, and then I want to make it a little bit harder, and I want to wait for you, because if you can solve the second problem that I want to tell you, it means that you really understand what is going on. Okay, but this one is simple, it's not hard. How many three-digit numbers, so let me write it down on the board. Example. Are there so that each number contains exactly 1/5. So I continue this. How many of them do contain at least 1/5? Okay, I want to give you a little bit of time to think about it, and then I will write one more for you later. The people at home, when I pause the video, you will not be able to see what I have written on the board. If you want to take some short notes from the problem, if you want to think about it. Three-digit numbers containing exactly one digit of 5, and how many of them do contain at least 1/5? That's the problem. So now I pause the video. Okay, do you have answer for the problems?
I have answered for the second one, but I don't have.
So how many three-digit numbers are there so that each number contains exactly 1/5? I don't know, how do you think about the problem?
To calculate the total and then subtract.
For exactly one?
No, for the other one.
Okay, yes. For the other one, you're right, but somehow. Let us answer the first question first.
Okay.
So if I want to calculate three-digit numbers, the number of items there, so what is your strategy? For the first part, if I want to define my task is to write a three-digit number so that my number contains exactly 1/5. Yes? So, how do you see the problem? Do I really need the sum rule here at all? What's the answer?
We use the sum rule.
We have to use, I think. Yes? So how do you use the sum rule? Assume that this is the whole category of items, the whole collection of items. So how do you think about the problem? Because you have to have 5 somewhere in your, yes?
So we divided it into 3 categories.
3, yes?
The first one is when you start with a 5.
Yes, so let me write. So you divide to 3 categories. This figure is not to scale, okay? So don't forget about the sizes. So here you will start with a 5. So it means that you have 5 and then you have 2 other options here. Or you put 5 in the middle, you have this. Or you have 5 here and this. First of all, are you convinced there is no overlap between these parts? Yeah, it is clear because these are starting with 5, but these have 5 here, nothing else. So they are not overlapping. Okay, now can you tell me how many items? Okay, here. So it means that 5 is here, so I have to choose these numbers. So how many options are for the first cross? 10. Sorry. The distinct digits are written. No, exactly 1. So I am not allowed to repeat 5. That's the only thing. So it means that I have to write 9 here. And how many options are available here? 9. Because I cannot choose 5. That's the only constraint. So this means that by the product rule, so far I have 81 items. Is that clear? When I go here, I start with this one with more constraints. How many options are available here? I am not allowed to choose 5 because I want to have exactly 1 5, but I'm not allowed to choose 0. We know about that. So how many options are available? 8. But for this one, how many options are available? 9. So the product rule tells me that this is 72. And I go here. How many options are available for this one? For the same reason 8, and for the same reason 9. And then I multiply them, it becomes 72. And then I have to add them. So what do I get?
225.
225. So there are 225 3-digit numbers, each containing exactly 1 5. Okay, how many of them do contain at least 1 5?
252.
I don't know. But that is the strategy, because I just want to tell you that if you want to use somehow the same ideas, I think you should consider a lot of cases, not a lot of cases, quite a few many cases. Yes, because you say at least 1 5. You can say I have 1 5, and then for 1 5, I have 3 positions for that 5. Or I can say that I have 2 5s, then I have again 3 scenarios. 2 5s, I don't know, starting with 2 5s, ending with 2 5s, or 5, the first 5, the last. So that's also 3-case scenario. And then of course I have 3 5s, which is clearly 555 with 1 item. But I mean that you have to consider different options if you want to use the sum rule. Yes, but now what do you want to use? Somehow might be the complement rule is better.
Yes, it is.
Yes, is it or not?
Yes.
So, of course, I am not telling you that the sum rule, if you write the sum rule, that is working and that will give you the full point. But for your own sake, I think it would be easier, if possible, to think about the complement rule.
Yes.
Okay, but then you have to be careful. How do you want to use the complement rule?
First, calculate how many 3-digit numbers there are.
There are, which we know. We have already calculated. How many of them are there? 900. So we know that the total number of items is 900.
Yes.
Yes, this you can use the product rule to find, or of course it is so trivial that we know there are 900 items there. But then we want to have exactly 1 5. What do you get? What do you subtract from it?
You mean at least 1 5?
One who doesn't contain any 5s.
The undesired item.
Yes, the undesired items are what?
The one that
Doesn't contain any 5. I want you to understand. Do you agree if I can subtract the numbers without 5s, then it would be exactly the answer to this question.
Yes.
Okay, so now calculating this item is easy because I want to have a number without 5. So from my list, I get rid of 5. So I have 3 options here, 3 stages.
Yes.
I don't have 5 at all. But for this one, I have one more constraint. 0 cannot be here. So how many options are there? 8.
And then 9.
And then it is 9 and
9.
9.
Because it's not.
Yes, because here I am not allowed to choose 5, I am not allowed to choose 5, but here I am not allowed to choose 5 nor 0. So that would be easier. But of course, if you use the sum rule, you have to consider 6 different or 7 different scenarios. So then it becomes 900 minus, what is that answer?
648.
648, and if you subtract,
252.
52. So your answer was correct. Yes. But of course, if you really want to learn combinatorics, you should also get the same number using the long way scenario. Yes, that is from my perspective, it is very instructive if you solve one problem from 2 different perspectives. Okay, now this is the problem I want to write and wait for you. It's not hard, but you need to consider different cases. And by the way, this problem is not trivial at all. So if I ask you this question before learning about these rules, I just want to mention that you see sum, complement, and the product rule are actually the rules that we have been working from primary school. But now when we look into them deeper, we actually can solve harder problems, which are not trivial at all. So how many 4-digit numbers are there that are larger than 4,721 with how many 4-digit numbers with distinct digits? Let me write it here. Are there so that let me show you. It's a very bad phrase, yes? How many 4-digit numbers with distinct digits and larger than 4,721 are there? So, I am interested in 4-digit numbers with distinct digits and larger than this particular number, 4,721. I want to pause recording and give you a little bit of time to think about this problem. It is not hard, but you need to consider some cases. Again, if you want to, the people at home, if you want to write something down, 4-digit numbers with distinct digits larger than 4,721. Any answers yet?
Yes.
Do you have it? What's the answer?
2,646.
What?
2,646.
2,600 I'm sure, but 46 I'm not that sure. Might be you have...
We are very sure.
Are you? How
We
are
also
you very
got
sure?
that.
You also got that?
Wow.
So might be that's correct, so probably I am not. Okay, so let us try to solve the problem. So what is your strategy to tackle this problem? So you are interested in finding, any people at home by the way, I didn't check. Oh, okay. So So you want to write a 4-digit number with distinct digits, which is larger than this number. So what are different scenarios? Have you used the sum and the product rule or a complement rule, or what you have used?
We used a combination of product and sum rule.
Yes, that is my strategy as well, because I wanted to solve it with the complement rule. I couldn't find a strategy to do that. Okay, so if you want to do it, you can imagine this is the total number of items that you want, but in how many partitions do you have now? So if you want to use the sum rule, you have to partition the whole items. How many?
Those numbers that start with a 4 and those that start with a number bigger than 4.
Bigger than 4. And so for bigger than 4, you can solve it with one case. I mean, you divide it into 2 parts with 4 and bigger than 4, or you have more partitions.
No, only those two.
Oh, really? So let us see how you do that. Okay, so you say that you start with 4, yes? So because I couldn't do that with 2 partitions. So you are claiming that you did the problem with 2 partitions, yes? What about you? So Zinura and so did you? So what is your strategy to solve the problem?
Since first we take 9,000 and calculate the number of digits that are larger than 4,721, and then when we get the number of digits, we
So you are using complement rule somehow.
Yeah.
Okay then.
And then we use the sum rule. We divide it into 2 groups. The first case when the
Okay, so it becomes more interesting. Okay, so let us no, because I want to first of all because I couldn't find a way to use the complement rule exactly in my mind. Might be I'm wrong. Okay, I will come back to you, and I was not able to do it with 2 partitions. I will come back to that later. Okay, so I want to hear from you. So you are partitioning into 2 parts. Yes, one are the numbers starting with a 4, and then you have 3 more digits, and then the numbers which start with number larger than 4. Okay, so it means that here I have 4, but this item is larger than 4. So let me write the options that you put here are 5, 6, 7, 8, 9. So let me write it like this. Either you fill this gap with 4, or you fill it up with one of these options. Is that what I understand? Yes? Okay, so now if that is the case, so how many options are available? Only 1. Okay, so let me write the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 4, I have to drop 4, yes? I have to drop 4. Because I won't have distinct digits. Okay, then how many options are available here?
3.
3 options are available here. What are they?
7, 8, and 9.
7, 8, and 9. So you have 3. So one of them are gone. Okay. And then?
Then we have 7 options.
Then we have 7 options. What are they?
2, 3, 5.
2, 3, okay. So 2, 3, okay. So 5 options.
No, there's 7 options.
So then it becomes a little bit not clear. Yes, do you agree with me?
6, 8.
Yes? But let us wait.
6 options.
6 options.
So you say 6 here.
Yeah.
Okay.
Okay.
Independent of what you have chosen here.
Yes.
Because when you wrote here 3, so let me so here you have 1 option. So let me write it like that. You wrote 3 here and 6 here. So I think I have a little bit of problem here, because when you say that there are 1 options here, 4, and then you say that you have 3 options, it means that, so let me write 3, 4, 5, 6, and 7. So why do you write 3 here?
Because it has to be 7, 8, or 9, since it has to be larger than 4,721. So it doesn't matter if there's a 4 in it or not. It's not
Okay, so what you're saying is that let us assume this case. You choose 4 for the first one. You choose 7 for the second one. Okay. And then, okay, so far I agree with you. You have one option and then you have three options. But when you write 3, it means that you have accepted 7, you have accepted 8, you have accepted 9. This is clear. But when I go here, then what do you say? One of these numbers is crossed over. 4 is crossed over from your list. And one of these numbers are also crossed over. Which one?
So it doesn't.
It doesn't matter. So if you say it doesn't matter, I cross this over. And then when I reach to here, what number you want to choose?
We accept 2, 3, 5, 6, 8, and 9.
Except 2.
2 to 9.
So you can choose 2.
Yes.
So this is 1, 2, 3. Yes. 4, 5, and 6. So you say 6. And then one of them are gone now. Yes. So, for example, I take this one away. And then what do you say? How many options are left?
Now we
We
have
have from 2 to 9.
Okay, so 2 is crossed. So how many options are there?
5 options.
1, 2, 3, 4, 5. This is what you have written. Yes?
Yes.
So you are saying that the way that you have done is considering all 4-digit numbers with a start with a 4, yes? And larger than that number. I am a little bit suspicious about that. Because you said 4, I put 4 here, that's good. And then you say that I want to choose 7 or larger.
Because if
I'm thinking.
we can still choose 7 if we can ensure that the last digit is larger than 1.
Yeah, I think I need to, because there is no time, and that's a good problem. I will come back to this problem. I want to detect the number. Okay, so everyone will think about this problem once more. Because the way that I did it, I wanted to divide it to 4 categories. I was not able to do it in that way.
Vad rimmar du? Okej, Amanda.
Den här för man är det.
Men metoden var där, okej. Så
Jag hörde också.
lägga på.
Jag vet inte.
Excited.
Vi är inte.
Jag är excited for arcade.
Okay, but the next session I will start with this problem. Of course, I will find the answer myself the way that I do it. And if the answer that you get is the same number, then it means your method is better because you are doing it with 2 categories.
I just want to correct your answer.
Yes?
2,610.
That is, I am sure, wrong. So what is your answer? The same answer?
Yeah, but I don't understand how
Because we did a mistake to include one more.
You are doing different strategy, yes? No, but I would say I don't remember exactly the number, but mainly I think both of you are wrong. And then the point is that I have to be able to detect what is the mistake. Might be my method will be, I don't remember exactly the number, but I want to do it into, that's a very good problem. And that's the nature of combinatorics, by the way. You should be a little bit doubtful all the time. We will start with this problem next time. Thank you.